Yes, good morning, good evening, good afternoon, everywhere. I'm Thorsten Höffler at SPCL at ETH Zurich, a professor here, as some of you may know. I'm super glad that we got Mohamed Wahib today from RIKEN CCS, one of the top research institutions in Asia and certainly the top in Japan. And Mohamed represents a nice group there, and he's going to tell us about scaling and deep learning on HPC systems in a minute. So giving to Nikolai to introduce him in more detail and looking forward to his talk.
Thank you, Thorsten, and thank you again, Wahib, for agreeing to give a talk here. Wahib is, I guess this is quite new, the team leader of the High Performance Artificial Intelligence Systems Research Team at the RIKEN Center for Computational Science in Kobe, Japan. Prior to that, he was a senior research scientist at AIST, and he had received his PhD in computer science from Hokkaido University. His research interests are broadly high-performance computing. If you've been to supercomputing, for example, you've seen his numerous papers, including best papers and so on especially using GPUs and making them go incredibly fast. And so without further ado, I'll let Wahib take it over. Thank you again.
Thank you, Thorsten and Nikolai, for the introduction. Shall I start? My voice is clear?
Yes.
Okay. So today, I will try to cover a broad topic, actually, that touches on different angles or aspects on scaling deep learning on HPC systems. Before I start, I have to acknowledge that much of the work discussed in those slides come with collaboration with an amazing group of people from inside and outside Japan, and without them, this work wouldn't have been possible. As Nikolai mentioned, a small self-introduction. Just last month, I started working back again in RIKEN CCS. I did work in RIKEN from 2012 to 17, and now I'm back again. RIKEN CCS, if you don't know, is located in Kobe. It's a nice city in west of Japan, very close to Osaka and Kyoto. They also have a satellite office in Nihonbashi, Tokyo, which is co-located with another RIKEN research center, RIKEN AIP or RIKEN AI project. And RIKEN CCS has always been a home to flagship supercomputers in Japan, previously K Computer and now Fugaku. The team I work in is high performance artificial intelligence system research team, which is located in Tokyo office, but we still have presence in Kobe. Includes a group of amazing researchers like Igarashi, Balash, Alex, and Emil, and hopefully we expand soon. Speaking about the challenges of AI and machine learning, again, AI is becoming an important HPC workload. And when we say AI and machine learning, there are different flavors of that, but particularly deep learning, and this is clear probably to everybody nowadays. So I will assume everybody has some knowledge or heard a little bit about deep learning. So I will not do any introduction for what deep learning is. HPC, as we know, is a study of bottlenecks. It simply goes down to that. When we look at the challenges of large-scale deep learning, we have to acknowledge there's two different categories. I might divide them, right? You can divide them as you wish, but those are the broad two categories of things that are more relevant that people should probably be aware of. So when you're looking at addressing or studying the bottlenecks of scaling deep learning, there are two categories you go into. Either you are restricted by underlying training assumptions, meaning that whatever you're trying to do, you just view the code running as some workload, and any of your optimization would not at all have impact on fidelity or accuracy. So this is a class or category of work that's important and touches a lot on the practice of HPC. And there is another line or a category in which you actually, while trying to optimize, you say, okay, I will also challenge underlying training assumptions, meaning that I will take those training assumptions, a training assumption, and try to question them or challenge them and propose something new. In this category, you must consider the impact on fidelity accuracy, and these kind of works you usually have to run into proving in a theoretical and empirical way the impact of what you're proposing on the accuracy or fidelity. I will try throughout the slides whenever I discuss any work done that I present or work that I'm commenting on, not our work, to distinguish between these two, one where you're restricted, one where you're not. Unlike maybe HPC workloads, which you probably can name typical famous HPC workloads that are bound by something or one bottleneck, actually large-scale deep learning can have different bottlenecks. It essentially boils down to how you define your scale, model, data set, and training strategy. Playing around with these things individually or together with each other can actually change your problem very much to make it, to run into bottlenecks at different stages. You can run into memory capacity bottlenecks, and this you can see from even a single GPU all the way to large-scale training. Same with I/O in medium to large-scale training, especially if you have a larger data set, it can be an issue. Communication is an obvious one when you go to large-scale training. Also compute, if you go to like the low-level substrate of operators you really rely on heavily in training deep neural networks, you can run into bottlenecks, especially if you have things like unusual matrices with respect to their shapes, batch matrix multiply, if you're using a lot of sparsity because it's a graph neural network or something. And finally, optimization-related algorithms, which you're actually bottlenecked by the optimizer, for example, itself, or by the hyperparameters or any pre-processing like augmentation and such. And finally, the one that I think is important that people have not been being, people always, when they say large-scale deep learning, they refer to training. And I think actually inference is going to be very relevant because people will not be forever training. The whole point of training is just to get models that work, then people can use them in the workflow. So at some point, people will more and more do inference in HPC settings. And we're speaking about distributed inference in this case, because these problems run typically in a distributed fashion. So you really imagine inference might be distributed also. And the game in inference is also latency, end-to-end latency. While training is about throughput, how much samples you can train per second, inference, yes, you can do them in batches sometimes, but sometimes you cannot, or sometimes you care about end-to-end latency, which is something that's important, but probably has not attracted as much attention as training. So those are all, not all the bottlenecks, but the main bottlenecks, and as discussed earlier, depending on how you define your strategy of training, the scale, the model, that's it. You can run into one or more of these bottlenecks. In this talk, I will try to briefly focus on some work we have done towards the first two. I will not focus on the remainder. We did have work on that, but I will focus on the first two, mainly memory capacity and I/O. So first, speaking a little bit about memory capacity image. People have been happy with deep learning distributed fashion doing what they call data parallelism, where you split the samples and processing elements. There can be issues with that. We have already witnessed, and it's an ongoing issue that people already know about very much, which models are very large, so you cannot fit. You can have very large samples like 3D convolutions. The samples do themselves not fit, or the activations do not fit. Or you want to simply increase your mini batch size, and then you have issues with mini batch size that are well known when you increase the mini batch size that relate to the accuracy and conversions. So you might want to find another way to parallelize. So what would we do for memory capacity, or if you have a memory capacity limit, you did observe. There are 4 things you can do. There might be more, but those at least are the 4 ones we looked at. One is just simply use more nodes and GPUs, and people actually do that actually. But I guess this is just an efficient way of using resources, to just use more GPUs or nodes just because you need more memory. Better can be done. So you have 3 more options. One is to go out of core. And this is something well known in the world of HPC. There are negatives. You're more sensitive to co-located workloads. Also tricky when you don't have high capacity memory to spill over to. Positive though, it just builds on data parallelism. You just use a good old data parallelism. You don't have to change anything. You don't change the model or the framework, and no messing with batch norm. And we had a paper on that a couple of years ago. The second option is to explicit model parallelism, which you explicitly say, I will split the model in a different way, where I extract my parallelism from how I split the model and not get my parallelism from splitting the data itself. What's good about it is that it's deterministic. You can do it ahead of time. Overhead can be low in many cases, not necessarily all the time, but it can be low. Negative points is that constructing cost models that is very accurate is kind of tricky. But also it carries a high implementation cost because you have now to split your model in a different way. Third option, we also had a paper on that last year in HPC. Third option is to partition the computational graph, in which you actually take your graph neural network and extract the graph, which is provided by frameworks like TensorFlow, which is very fine-grained. And then in this case, positives are it's agnostic. Actually, this is the best thing about it. It's not like explicit model parallelism where you have to be aware that you're actually it has a high implementation cost. Here, you're not aware because you just intercept the graph and split it. And it can leverage the HPC graph knowledge about how to handle graphs and how to partition them into resources. Obviously, the issues is it's dynamic. I mean, it depends on how many nodes you use, for example. Also, it's likely non-deterministic. You have, what the heuristic you use actually to split the graph. And we did have a work on that. So I will try in the next few slides to cover a little bit of each one of them. First, I will start with explicit model parallelism, because I think this is where we learned a lot of lessons when we addressed that work. So in that work, we proposed what we call an oracle. And the assumption was that there's different forms of model parallelism. I will cover them in the next few slides. What we tried to do is to provide some model-driven analysis and a utility also that allows you to detect limitations and bottlenecks if you use a different type of parallelism approach at scale. So the goal, as I said, is to formally define those parallel strategies and have a comprehensive analysis and use that to essentially build a performance model or an oracle that tells you, given this model, given this data set, given these resources, this is how you would want to extract parallelism, or this is the type of model parallelism you want. And we fairly evaluated a large scale, more than 1,000 GPUs, V100s at that time. And actually, we did see that ParaDL is kind of decent with respect to the accuracy and performance prediction. And actually, it did help us to find some inefficiencies in frameworks and also in the method we use. Again, the motivation was that there was no way to determine what is the right parallel strategy. People would pick up some given model based on its how it looks like, based on the constraints of, for example, not fitting in memory or how the data set looks like, and they decide just to use one of the parallel strategies without actually having a method to guide them. Too much time is spent actually trying different strategies, and even a strategy might be obsolete as soon as you move to a different, or if you care about portability and if your model changes or the system even changes. So the strategies, just to summarize, they're one of the following that we know of: the data parallelism, which we explained before; channel parallelism, which you're dividing your channel; filter, which is related very much to channel; spatial parallelism, where you're splitting the model in a horizontal way; layer parallelism, or pipeline parallelism, as you call it, where you're splitting the model in a vertical way; and then hybrid, in which you combine 2 or even 3 of the above methods. One thing that's interesting, actually, that people might not take care or notice, that actually people assume that data parallelism was always how people did it, and then they just moved on to model parallelism because data parallelism was not enough, or you had issues with memory capacity. Actually, if you look at AlexNet, which is in 2012 started all this interest in deep learning, it actually uses model parallelism. It had 2 GPUs and it split the model in a horizontal way on 2 GPUs. So actually, distributed deep learning training started out as model parallelism, and just people moved on then to data parallelism because of the convenience of using it. And now we're back again to model parallelism because of the limitation of data parallelism. There are many strategies. This is just a sequential model, which you start with samples, you go through the layers. There's data parallelism, in which you're essentially dividing your data set, and you keep a replica of each model and each processing element, be it a GPU or a CPU. And this carries an all reduce in which you do the gradient exchange, because in this case, you want to make sure after each iteration, all processing elements keep the same version of the model. There's also layer parallelism, in which you're splitting the layers themselves in a pipeline or spatial. The pipeline is where you split your model into layers, and then you pass on these layers into different processing elements. Spatial, in which you're splitting the model from the middle, like as AlexNet did. And you have filter and channel parallelism, where you actually they're more or less close to each other, and they both look at it from the perspective that your parallelism comes from the fact that you're applying different filters to get your feature maps, and you can just split your filters or split your channels. And then there's a hybrid. So one result of that work is that per epoch basis, we try to analyze the compute communication and memory required and limitations on number of processing elements, so that we know actually at least how to say speed of light, what is the minimum requirements or maximum actually in this case for memory that you need for every type of parallelism to at least have this Oracle or cost model that we can then plug in these numbers and try to figure out which one is better in which case. Based on that, we had this Oracle in which you just specify how the data looks like, sample size, number of samples, also how your model looks like, essentially the shape of the model, the layers, complexity, flop counts, etc. You can extract that. Actually, there are many tools now that extract this by static analysis, or even now PyTorch and TensorFlow can give you a lot of that information. There are APIs for that. And last is a computer system specification, which you pass down how your architecture looks like, interconnect hierarchy, the bandwidths, and also how the processing elements themselves, be it CPUs or GPUs, look like, the memory capacities and flops and such like that. And then it would give you the best parallel strategy for this combination, like of data set, model, and system under some constraint. If you care about compute time, it tell you, okay, if you care just about compute time within this resource budget you have for this model, pick this model parallelism. If you care about communication time, take that. Or if you care about just max memory per processing element or maximum number of Ps. So essentially it adapts to your needs. And the whole purpose of that is that you don't have to go back to the board again every time you change your model or do or have a new system to decide which mode of parallelism to use. We actually tested with a variety of models, ImageNet with different models, and CosmoFlow, which is one of the data sets now in ML part of HPC. And it represents, we kind of emphasized on it because it actually represents how HPC work, like data sets look like, in which you have 3D convolution required for CosmoFlow. So each sample is pretty big, and actually just passing CosmoFlow through the first layer, you can't even store the feature maps for it, just doing the first layer of convolution. So, and that's even for a single image. So you have to split it. There's no option here. First, to get a sanity check, we checked the accuracy of our predictor against data parallelism, because this is we know very well, and we had encouraging results approaching close to like more than 90%, 95% on average, I think, all the way to 1,000 GPUs. And this was kind of a relief for us because we knew at least our model works correctly for data parallelism. And we, of course, separated the computation from communication just to make sure that to track if there's some inaccuracy in our prediction, where does it come from? Is it communication or is it computation? Then we again tried to confirm this channel parallelism this time. Maybe the numbers are quite lower, not again as data parallelism, not the 90% anymore, but still it's reasonably high enough that you can at least get some, first order number from which you can figure out if channel parallelism makes sense or not. Pipeline after that, and I think, again, it was reasonably good. Pipeline because we focused on intra-node parallelism, so the number of GPUs per node, and the maximum we had in our system was 4, so that's why we go only to 4 GPUs. There are works, including the paper from the lab you have. We had an SC last year, in which I think it used baseline that uses multi-nodes, so 1 GPU per node. Probably that's the only work I know of. Most works in pipeline parallelism was just within 1 node. Hopefully you want at some point to extend the analysis to cover also multi-nodes, to go beyond just nodes in a GPU, GPUs in a node. And then we try to look at every variant. So essentially, our goal is 2 things. First is to see how accurate is our predictor or oracle, and number 2 is to see if there's if there's a discrepancy. Essentially, if we're projecting something but we don't see it, why is it happening? Is it something wrong in our cost model? Is it something wrong in our assumptions? Is it some inefficiency on the framework itself we're overlooking? They do something that's inefficient, the implementation we can't catch. So this was the whole point, not just to show its accuracy so that people can use it later on, but also for us to use it as a learning tool to know what's up. And for that, we had, at that point, it was really tricky in the sense that most of these modes of parallelism were not implemented in PyTorch or TensorFlow. We use PyTorch, by the way. So we had to implement it with our own hands. Nowadays, you have some implementations. For example, you have the pipe dream, pipeline parallelism is upstream now in PyTorch, so you can use that, for instance. At that point, again, like a year and a half ago, we had to implement them, which took some effort. And then again, the purpose was just to see how far off was our prediction, and also to know if there's things. Why is this discrepancy, or would that tell us something or not? Did the same with CosmoFlow, and that was a particular case we cared about, and it uses spatial parallelism. And it took some effort for that because CosmoFlow was not an easy data set to work with. Especially that you can actually increase data. It's kind of, you can think of data set as 3 synthesized. You can synthesize the data set, so you can easily have 128 cube, 256. Now there's 512. So you can really scale the sample size if you want. And this stresses different parts actually when you want to go with. To summarize, I think this is essentially the walkaway message from that paper: is limitations in the scaling itself. We started to look at communication, memory, capacity, computation, and scaling, and we started to see the parallel strategies, like data parallelism, spatial, pipeline, filter channel. This is hybrid, which is data filter or data spatial. And we wanted to see essentially if there's an issue with a framework or issue with the system. Are we seeing some discrepancy or some limitations the system is not allowed us to scale due to some issue, or do we see some issue with the framework? And we tried to identify which points that we can take off. And we looked at different training phases. I/O, which is becoming increasingly an issue now. I will cover that in later slides. The forward and the backward, and granny exchange, and the weight update sometimes can be a bottleneck. And we started to look at it, how it looks like, and also we looked at inference a little bit. And even though it was dedicated clearly to training, we also thought, why not look at inference to see if any of those issues can be limitations. That's why there's N and Y, no or yes for inference. I refer you back to the details in the paper on how those limitations were there. I'll just cover a few points from them in those slides. So for example, for memory capacity, at that point, we realized there's a lot of redundancy. For example, activations are distributed, but weights are not. But since then, again, a year or so, a year and a half has passed since that work, and that's a long time in this area. So PyTorch had it sharded data parallel. Also, there's a lot of effort by DeepSpeed 0 and its variant 002, 0 offload, 0 infinity, in which they're exactly trying to do that, remove any kind of redundancy, which is not necessary. Memory manager, we realize also that there are cases where you have stalling because memory management is not so good. Because you might see some form of fragmentation or so, or keep on, allocating memory and releasing it again and again. So you needed some form of memory manager where you pre-allocate memory to some granularity and just manage the memory in a way. We did identify that, and we mentioned that in the paper. And actually, NVIDIA also did at some point in CUDA 11.2, quite recent, I would say a few months. They introduced what they call asynchronous memory, and essentially it's a memory that's pre-allocated, and you can just ask for buffers. You can ask for memory regions in it for your buffers and release back again, and it maintains this pool of memory on your behalf. One other point, compute. Again, we realize that the weight update can be a bottleneck in some cases. Like for example, in this figure, we realize that sometimes it can go up to creep up to 10%, and in some cases 20%. So even though weight update has not been really viewed as a computational thing, bottleneck, usually people mention forward and backward grand update, but we realize at some point it can be an issue. And the good news is, again, quite recently, Google introduced a work called G-Shard, in which actually is trying to kind of address this kind of point to make the weight update more efficient. Workload balancing, and when I say workload balancing, I don't know just mean balancing the work, but balancing the memory actually, because we realize that pipeline performs better than data parallelism because there's peer-to-peer contact. But if the pipelines are not balanced in their work, you obviously create some form of bubble in your or stalling in your pipeline. That can come from imbalance from the work, meaning that not all GPUs or PEs have the same amount of work, but also from memory. But some of the PEs are stretching so much in the memory capacity that they're pretty much becoming late, not because the amount of work is more, but because you just ran out of memory. So you have to wait until there's some free memory. And we realized this point that, to my knowledge, is maybe not so solved 100% yet. Maybe there's some papers recently, but to my knowledge, this has not been 100% solved yet. There have been papers that push for better pipelines and better fitting in the pipeline, and including the paper, again, from SPCL in SC. I'm speaking here about load balancing. We realize there's a lot of computational redundancy. The frameworks, we're making assumptions on the cost model, and then we find discrepancy and we investigate the code. We look at the implementation overhead. But I would say this is mostly being resolved because frameworks now are pushing in every release. They're refactoring the code and trying to optimize it. And this was essentially the walk-away message of this paper. We go back to the main slide in which we said there are three ways at least the main message we care about. There might be other ways, but there are 3 ways or 4 ways, including inefficient use of resources, in which you would want to address the memory capacity limit. The first one we discussed was explicit model parallelism. Second was out of core. We had a paper on that in SC a couple of years ago. I will not go into details for that paper for the sake of time, but I'll be glad after it or offline or in the Q&A to discuss more on it, because I think the last message is maybe more relevant because it touches on graphs, and I know there's a lot of interesting graphs in the group to extent, so people might be interested in that. So for that one, I'll just have one master slide that just says that what we call karma, which is essentially a way to go out of core. It was at that point a new strategy for out of core. Essentially, the whole point is try to keep enough concurrency for GPU to be busy. It's driven by a concurrency cost model. So as long as you have enough work for the GPU to do, go aggressive as you can and out of core. And we had what we call capacity-based interleave with recompute, meaning that as much as you can go out of core, do the swapping aggressively with the CPU, and interleave that with some calculated recompute, which you recompute in the backward pass, again, the activations, in order to reduce any stalling you would have in this pipeline of training. And at that point, we got over the state of the art 1.5x on a single GPU. And what important, it was at that point the first out of core for multi-GPU, which is an issue because if you're doing an out of core method, that means by definition, all your layers are not on the GPU at the same time. Because if it is, then you don't have a memory capacity issue. So if you're doing out of core, it means not all your layers on GPU, some are CPU, some on the GPU. So you needed some way in which you can do the weight updates and manage the gradient exchange while having your data being between the CPU and GPU. And for that, we introduced some heterogeneity and orchestration to be able to do that, a 5-stage pipeline essentially to do that. And even when just comparing with data parallelism and model parallelism with out of core, we experimented up to 2K GPUs, and the results were quite good. Again, I will not cover details. If you want, I'll be happy to discuss later in Q&A or even offline or by email or so. Just a walk-away message from this out of core thing is that since then we have been seeing production quality solutions because again, karma was restricted in a sense. It was, I wouldn't say production quality, because the main thing was to show that this works, and for the models we tested. So we took some shortcuts and hacking to the PyTorch itself to make it work. But since then, there have been production quality solutions. I mentioned an example of them is zero offload, which is essentially doing exactly what karma is. It can work on a single GPU or multi-GPUs, and it allows you to just swap in and out your layers, to relax a little bit their memory capacity stuff. And I think it's a matter of time, to be honest, until we see it upstream in frameworks like PyTorch and such, in which takes care essentially of that. And one interesting thing or food of thought is, can this concept be used in multimodal training in neural architecture search? Meaning that not just use it as a way to relax memory capacity, but if you're in parallel evaluating ensembles of neural networks, which you're changing the model as you have a search space of how a model looks like. It's a neural architecture search regime. Then you have different variants. So can we use it where we're swapping layers of different models in and out, in which you have, for example, model A and B, they have a common subset of layers, and then they diverge in other layers. So we can swap the layer such that fix a common layer so both of them see it, and then swap out the difference between them. So this is, I think, a direction where just out of core can be applicable and it can add something. Go back again to the master slide, or again, we're still with memory capacity issues, and this is the third approach we looked at, in which we partitioned the computational graph. This was a work by Farid, who was a master student at the time in Didem Onat's lab in University of Cook. I think he's doing now his PhD in Chalmers. So this is an interesting piece of work because we have this parallel or parallel. It's generic. So I kind of like this approach because it's quite generic, because there's zero dependency and you require no knowledge about the deep learning aspect of the model at all, unlike model parallelism or out of core, in which you kind of essentially have to be explicitly aware that either you're swapping layers in and out if it's out of core, or you're splitting the model if it's model parallelism. It's quite automated and non-intrusive also. You don't feel anything. You don't have to change your code at all. You don't need to modify the model or operation kernels, or you don't need to swap layers in and out or anything. It works at a lower level hidden from the user and operates on the computational graph. So essentially, deep learning models can give you a computational graph, specifically TensorFlow, because it's what they call define and run, in which you define your entire graph and then it runs. Even in frameworks like PyTorch, which has defined by run, and nowadays can allow you to run and capture the graph and intercept and get that graph. So essentially you have a graph that represents this. This is a fine-grained graph where don't in your mind translate it that each layer, for instance, is one node. No, this is much more fine-grained. So even if you have a small model with few layers, it translates to maybe hundreds or even tens of thousands of nodes in that graph. And this graph is pretty much left to the framework. Its definition is quite weird. For example, it can include, in TensorFlow's case, nodes that are computation, and some are just conditional nodes. So it's not your usual graph, but anyway, it's a graph, and graphs pretty well. And it includes both the forward and backward paths. So beginning to end is like where you start from, it goes flow through the operations, and then it includes the forward and the backward. So it's the entire training thing. Including the gradient update and everything. So that's the entire essentially iteration represented in that graph. This graph is static if your model is static, essentially, right? There are, of course, areas in research that look at in more dynamic graphs or masked gates or something like that, which changes the graph as you train, or for example, method that sparsify while you train. Like the lottery ticket hypothesis, in which you sparsify and you reset the weights. But for that work, we assume that the graph is static, has not changed. So it's constructed before running stays the same. Again, though we acknowledge there are dynamic cases. This graph is acyclic, as you would imagine. And as I mentioned, it's not made up of it doesn't translate to just one node in a neural network or one layer translate to one node in a graph. This is very fine-grained. For a mid-sized neural network, say ResNet 50 or so, which is nowadays mid-size or even small size, but currently you might have tens of thousands of nodes, even hundreds of thousands of nodes. So once you get this graph, this is now a graph, and this is what people know in HPC very well, which you have the vertices represent some tasks, some work is being done, and then there's communication between the nodes. And the good thing that this graph that you get from TensorFlow, or I guess from other models, NextNet or so, other frameworks, you can extract the dependency and you can extract what's being exchanged exactly to know exactly the communication time between the nodes. And it also defines the execution order, of course. So what we did is we made a cost model that does online profiling to know how much compute would be in each one of those, how much communication time, those are estimates. And we emulate the scheduler. So originally, when you want to take that and run it, there's an internal scheduler in TensorFlow, and I would imagine other frameworks that run schedule that for you. We would emulate that, and then we generate the graph and do our own splitting now. So we partition it. So, for example, we might have two different GPUs in this example, one that takes the green nodes, one that takes those pink nodes. And then we do the mapping and we intercept what TensorFlow is doing and say, so node 1 in the graph or node B goes to device 0, node C device 1, and so on. And then this is essentially the mapping. This is what next TensorFlow or any other framework, I guess, can just take that and just assign and follow what you did. So it boils down to essentially graph partitioning. So just to imagine, again, I told you those look like very elaborate. So even if you just in TensorFlow define two simple variables and add them, right? So you're defining two variables and adding them. You're not defining a full model or anything. This translates how this graph looks like. Because again, it's very fine-grained, includes a lot of operations. So again, this is a very fine-grained graph with so many operations. Our objective, of course, obviously, is to minimize execution time. So we have distributed training, we have GPUs. In this case, we focus on GPUs. I would imagine this can be also expanded to if you're training with CPUs, like let's say for Apple. So let's call them PEs, processing elements. So the objectives try to minimize the total execution time of this graph you got from some model on some budget of PEs or GPUs or CPUs. Where you balance the load, obviously, and reduce the communication. It's a good old classical graph partitioning that we know very well in HPC, while also meeting the memory constraints of the GPU. So this is also a big issue. So when you split the graph, if you just, plus I would say multi-objective, if you just balance the load and reduce communication, you will still run into some issues with memory constraints. So you have to be conscious about that. Just to give you a feeling of how these graphs look like, they're not pretty small. So for instance, the models we tested when in the paper, like WRN, 3D LSTM. So for example, we had a small transformer. I would say small was today's definition of small of transformer. So one was about 2 billion parameters, the other was 5 billion, which is again, pretty small for a transformer nowadays. At that point, a year ago or a year and a half ago, that was reasonably sized. But even just that relatively small transformer was 5 billion parameters. It had a graph of 160K nodes. So you would imagine if you would take a large transformer, I don't know, 175 billion parameters, whatever the largest transformer nowadays, or 500 million or so, or 500 billion, sorry. The largest we heard about that's reported. You can imagine how the graph size would look like. We're approaching like very large graph sizes that we typically see in HPC. But even again, with those moderately sized models of the parameters are mostly around 1 million or so. Maybe a billion, sorry, maybe less than 1 billion in some cases, maybe more in this case. WRN was more, transformer is more. We had two variants of eidetic three-dimensional LSTM, but more or less, again, the number of nodes were pretty huge in this graph. So that was an issue on how to split it. So essentially, what you could have thought of is just take any off-the-shelf or any existing solution for graph partitioning and just use that. But we realized that this doesn't obviously give the best case because those are usually generic or designed to work with any graph. But we have knowledge of this specific graph that allows us to have our own heuristic to more optimally partition this graph. And our work essentially was made up of 2 steps, applied one after the other. So rather than having a multi-objective optimization that has single optimization problem, we did 2 steps. So first, giving K devices a partition the graph, that execution time is minimized. reduce the communication time between nodes, and also load balance your computation. This is pretty straightforward. The second is, after you do that, you might run into cases where you do not meet the memory capacity limit after you partition. That's where we do our refinement step, in which each partition we check if it's under the budget. Okay, if not, then we had a heuristic. It's fully detailed in the paper, and also have backup slides if you're interested to know about both steps. Anyway, so it handles the memory overflow by moving some of the graph to the other one while maintaining locality parallelism. I will jump here right away, even though there's so much technical details, but they're all again in hidden slides. So if you want to know more about that, I would be happy to explain more on both of them, like the first one and second one, what kind of heuristic we had. Simply speaking, we just found critical paths and we started to cluster the critical paths together, so that each set of critical paths or cluster would go to one device. This is essentially the approach we used. First, identify critical paths, and then make primary clusters, and then secondary ones, and then we assign to devices. For the second one, what we did is we modeled the memory, the scheduler, or emulated the memory allocator used inside in that case, TensorFlow. Of course, if you use another framework, you have to do it for that also, in which we handle this memory overflow by moving some of the nodes until you balance out or you meet your memory, your hard memory constraint, while still maintaining some reasonable also computation overload, and always minimize the communication time. I think the results were quite good. We tested several models. Again, not very large with today's standards, but a year and a half ago, they were pretty fairly not small. And we use a DGX2 that has 16 GPUs. Obviously, we would want to take that work and make it work on multi-nodes, or take, for example, a CPU-based system like Fugaku. That would be nice. Or even a system with GPUs, like let's say baseline with 1 GPU per node, and you would want to scale that to intranode. But in this case, we will all intranode. So assume all the GPUs are inside one CPU, which is a DGX2. One thing you have to look at is also the properties of the graphs. For example, two metrics we looked at: degree of parallelism, which just mentally imagines the width of the graph, how much parallelism you can extract, and computation to communication ratio. We found that there's no correlation. So it's not that because you have higher degree of parallelism, it would affect anything about communication to computation. It's really very much model dependent. So you can have low degree of parallelism, but very high communication to computation ratio, like in wide residual network, or it could be like same with transformer, but or it could be also like eidetic, like 3D LSTM, where you have low degree of parallelism, but also low communication to computation ratios. I think in the paper, we also went into other metrics to describe those graphs. I think one nice extension or to build upon that is to actually run state-of-the-art models and generate those graphs for them, and have them as a set of graphs available to everyone to test their graph partitioning methods, in which you can, again, in an agnostic and transparent way, split the model in different nodes, or PEs, be GPUs or CPUs. But at that point, we looked into some of the metrics, just trying to understand how these graphs look like. And our conclusion, at least for the models we looked at, is that the graphs look very different from each other. You cannot, say there's a group of graphs that look like each other because how the model looks like. It pretty much depends on the model and how it's defined. Also, we had each of the steps I mentioned. One is to actually partition, and the other is to meet your memory budget, or satisfying the memory constraint. Each one included steps within the steps. Here where we include the slicing, the mapping, and refinement, and so on. And we tried also to maintain complexity that's comparable, or even better actually, than known or very mature ways in which you can partition your graph, like dynamic crystal paths or linear clustering or something like that. More details on that on the paper. And actually, even empirically, not just if you look at complexity, empirically, it was reasonably small. So for all our algorithms, the experiments, we were running less than 2 minutes. So that's nothing, of course, if you compare it to how much time you take when you train. So when you train, usually Even in that case, we had a DGX with 16 GPUs. Even in that case, you might expect to train for hours or days. So taking 2 minutes or so to partition the graph is not a big problem, I think, not a big overhead. We also wanted to make sure that we're not just performing better versus other ways to go beyond memory capacity, but also compared to the existing clustering or graph partitioning methods to justify why we actually need our own heuristic and not just using something off the shelf. So we compared with existing solutions like CP, critical path, and also over linear clustering. And we've seen like some reasonable speed up in this case of what we generate. This is not the speed up as in the time it takes to do the partitioning, the overhead. This is the speed up as after you partition and you train, how much time you take. So 1.4 speed up means that you're 1.4 times faster. The generated partitioning enabled 1.4x times faster training. So just to make a note of that. And in some cases was pronounced actually in transformers. It was much better in this case. I think it relates to how the transformer looks like. To be honest, we didn't really investigate specifically why in transformer this was the case. I think this is also probably a future point for future work. We also wanted to see, okay, how it looks like over a single GPU, over if it's weak scaling and if it's peak performance, to see how we scale essentially for the number of GPUs, because we cared about that. So we went from 2 to 16, 16 is the max, to see how we scale when we use our method. In some cases, it was very nice scaling. You go to about 15x when you go from to 2x. When you go to 16 GPUs, in some cases much less. But then we compared also, I guess, this way over ideal data parallelism. I think this was the comparison here. And we realized that we also allow larger data, pushing larger batches, because essentially, since now you're splitting the graph itself, you don't have the issue with data parallelism that when you increase the mini batch size, the activation size blows up and you run out of memory. In this case, we could increase so much over the actually data parallelism, and this is what we define here as idle over idle DP. So with 16 GPUs, we could go with exactly 16 times the mini batch size before there's issues. So which I think is a quite nice thing, that it can be useful also if you want to relax the issues you have with mini batch size. I think this is a case where again we're looking at throughput per peak performance and also per week scaling, and as we scale up for the model size, results I think were, sorry I jumped past it, results I think were quite promising in this case. Also we wanted to compare with other types of solutions out there that allow you to relax memory capacity issue, and one of them is to use gradient checkpoint, which is recompute essentially plus data parallelism, in which you don't store your activations. You just, when you go on the backward pass, you recompute your activations again, and it's a well-known strategy to relax your memory pressure. Even then, when you compare it with that, there were cases we run also out of memory, even with gradient checkpoint. That's because gradient checkpoint is on the order of square root of n being the number of layers. So you can easily, even transformer in this case, you can easily run out of memory, even if you use the gradient checkpointing. And it actually did fail a lot, actually. We also compared over mesh TensorFlow. So another way, again, we actually explained earlier that model parallelism is a way to relax memory capacity issues. This is one of them. Mesh TensorFlow is an extension of TensorFlow, at least at that point it was. I don't know if it's pushed now upstream to TensorFlow or not. And it's a way where you just spatially split your model and you even explicitly control it. So for example, if you have eight GPUs, you can say split your model 2 by 4, for example, the dimension of 2 by 4, and split your model in this way. And then underneath mesh TensorFlow takes care of splitting them and do everything. So we wanted to compare with it also. We did find that speed up, we actually outperformed TensorFlow in, I think, almost all cases we have found. Bear in mind, in mesh TensorFlow, you're still burdened with the task of finding the best way to split your model. So essentially, what we report here is that we manually used all possible combinations of how, or permuted the ways where we can split the model, ran all of them, and we picked the fastest one to report. While in the case of RDNN, you don't need to do all of that because, again, it's all transparent and hidden. It's all agnostic. And even with that case, mesh TensorFlow can go out of course, so out of memory. So anything in red here is essentially mesh TensorFlow still going out of memory, even with split the model. We also wanted to compare with out-of-core methods again. So we tried to diversify our comparison essentially to not just graph methods, because we haven't found, at that point we wrote this paper, graph partitioning method. We found one workshop paper without the code. So that's why we emphasize comparisons with model parallelism and also out-of-core. So we compared to CUDA unified memory, which is a unified memory is a technology that allows you to use CPU and GPU memory. They don't share physical space, it's just a logical sharing between them. And then all the swapping in and out happens by CUDA runtime. And as you expected, because of course it's not ideal, and that's the reason we proposed Karma in the earlier paper to begin with, the speed up was pretty across the board consistent all around, I guess, because CUDA unified memory is getting so much just page faulting. So to summarize that work, what we did is we addressed memory constrained deep neural network model and multiple devices. It's non-intrusive and model agnostic. It's a two-step algorithm to provide efficiency and low overhead. It outperforms our solution, and actually it's more practical. So among even the three things we tested, model parallelism and out-of-core and graph basement, I think this one, in my opinion, is actually it's not getting so much attention. People, there's tons of work on model parallelism, and there's a lot of work on out-of-core, but not much in graph. And I think this is the direction people should be probably looking at. How are we doing time-wise, Nikolai?
We are approaching the end of the hour.
Really?
Yeah.
Okay. I have a few slides on very recent paper on I/O. They're like 10 slides. It's up to you. If you want me to talk about them, it's okay. If you don't want, we can stop here. It's fine for me either way.
Go for it.
Okay, so you still have some coffee in your system. Good. Okay, so here I'm switching gears. I'll make this fast because I'm very sorry it took so much time than it should have. So we're going, this is early, again, as explained in earlier slides, there can be bottlenecks in different things. And one thing we realized actually when we did all this memory capacity work, that I/O can become a bottleneck. And this is recent work we have been doing to motivate it. Those are the top systems, 15, I think, right? I think maybe 15 or 12 of the top systems you have in the top 500 list. And we're just plotting here. What you see is the capacity of local storage or a flash storage. So if it's light blue, it's flash storage shared across the network, like in Fogak, each 16 nodes share some one tier of storage, or it has a local SSD per node. And we just plotted the big data sets we know about. Actually, this is like a year, not a year old. Maybe this is like 7 months old. Now you can add a lot of vertical, horizontal lines with much larger data sets. Especially there's synthesized data sets coming on, where people just make data sets from fractals or bands or whatever. There's the Lion data set, which has, I don't know, 5 billion images of pairs of text, like clipping images and text. So anyway, this demonstrates that most of the data sets would go beyond what you can fit. And by the way, this is, I think, is this is a log scale. So that means those data sets are really far away from you can fit. So essentially, this is a problem, right? This is a bottleneck. You have those large data sets and you want to train. So what would you do? And we did actually test a little bit to see also what's the impact on the parallel file system. And we did notice that actually really hammering the metadata server, because you have a lot of these files. People nowadays do some tricks. They try even to tar bold files together or combine files together to reduce the number of files they're moved, but it can be an issue. And we used Darshan to profile those on ImageNet 1K and 64 nodes just to see what's happening. And the parallel file system sustained aggregate bandwidth is 70%, less than the local SSD in this experiment, again, because of the metadata server bottleneck. So what we propose is data shuffling in a way. So I know there's a very nice paper, again, it's Nikolai himself that had about this issue. And this is where the difference comes from. I mentioned in earlier slides where you would have cases where you restrict yourself to what the underlying assumptions are. And this was the case in Nikolai's paper. He assumed he's not interfering with how the samples are being selected to train, but just because you know ahead of time the order by which you will visit, because you share the seed, then you can in a smart way hide this transfer of data. In this case, it actually challenges the notion that do I even need to maintain uniform access to all my samples? Because the assumption is you have your samples, you run uniform sampling, which you pick the samples at the a uniform distribution and use Fisher-Yates algorithm or something like that. In this case, we said no, we do shuffling, and by shuffling we mean that we split the samples. So global shuffling means every node sees all the data set and picks from all the data set. Local means every node sees a subset only, like in this case, and can select from its own subset. And then we can do local partial shuffling. Local means that each node gets a subset of the sample, but can change around some of the samples if need be. I will skip that and go directly to the results because it doesn't make sense. And here we experimented for fairly large scale up to, I think, 2K GPUs, again, for a variety of data sets. And the issue is we found that for local shuffling, sometimes sufficient. Sometimes you don't even need to make every single, this is, of course, data parallelism, right? You don't need every GPU or every node to see the entire data set. If it just takes a chunk of data set and trains with it and just samples from it, it just arrives at the same accuracy or mostly at the same accuracy as if it's global. Global here meaning that it gets entire view of that of the entire data set. We found that also is the same case if you do pre-training or even go for small models or large models. Then we found the case, and this is typically when you increase scale or you increase essentially you increase this, the number of nodes, so you're getting a smaller chunk of the data set size. This is where in the partial local shuffler, where you're partially doing some shuffling in between. And this is where you even see this gap. So you have the global as black and local is yellow, which is at least because you're suffering now, your accuracy is suffering. But as you do 0.1, meaning that 10% of the samples are swapped between nodes, or 0.3, you're getting closer and closer actually to what you do globally. And I think this was a nice result because it shows that you don't really need to share the data set. Each data, if you don't have a local SSD or if you don't have enough local storage to maintain an entire copy of the data set, you don't need to do that. Just keep a local part of it, train with it, and that's it. We'll skip because of the time again, and all these just show a little bit. This is training time, so performance. It shows that this translates to improvement in performance. That in global, you of course have training time is fast, but of course, as you do partial, so only exchange 10% of the samples. You start at large scale of 2K GPUs to approach what you get with global, in which you're just splitting the nodes among those 2000 GPUs and only do 10% swap around. Summarize, this is again is global shuffling has severe IO implication. It's not even a solved problem yet, and this work is just barely starting in it. Most existing studies just optimize for global access. It assumes that there's global access without actually questioning the importance of shuffling itself. And this is what we try to do in this paper partially, to build a library that allows to do this partial shuffling. And with that, I finished. I'm very sorry for overrunning my time. Hopefully some of that might have excited you. We're expanding the team, so it's a shameless plug. If you know anyone who's interested, postdocs, researchers, or even internships, we have those, including remote ones, be it in Riken, Kobe office, or Tokyo office. So if you fancy life and research in Japan, or if you know someone who wants to, please feel free to contact me. And you'll also get to play around with Fugaku, the world's fastest supercomputer. With that, I finished, and please, questions if you have.
Thank you, Wahib. I think the extra time was well worth it. Thank you. And before we move to questions, just a quick announcement that our next BCast talk will be on the 2nd of June at 6 p.m. Zurich time. So unfortunately, 1 a.m. for you, Wahib. And we'll have Mary Hall of the University of Utah here.